So the backward view of TD lambda makes this all possible to compute it in a more efficient way. It's quite clever, actually. So what we're going to do is we're going to build something called an eligibility trace. An eligibility trace is just a count, a decaying count that basically records how long it's been since we visited a state, right? And so I say it's an account, but it's not an integer. It's a continuous trace or measure or counter. But you basically, whenever you visit a state, you set it to 1, right? Or you increment it by 1. So if you've never visited a state before, then it becomes 1. And it's like this spike, right? And then every step you go, every time you update your value function, you decay all the states down, right? So this is a measure of a particular, this is ES for some particular state S, this view of it would be. And all of these lines here would be the times you visited S directly, right? And so it got a little spike, went up by 1, and then it decayed down. And here we didn't visit it for a very long time, and then we visited it again, and it went up and down. So why would we do this, right? If you think about what we're doing with the n steps ahead, we say, you know, we're going to decay it by lambda for how many steps ahead it is, but we're also going to use that value and have all these kind of weightings, right? And so the further ahead it is, the less we want to kind of use its reward to add into all the returns going back. And I mean, that seems similar to gamma, right? Because in gamma, we're discounting future states, but that's kind of how important those updates, those values from future states should be on our current consideration. So they seem related, right? They're about kind of downweighting points in the future. And so when we use this eligibility trace approach, we're basically going to have both of them, right? Because we're still going to specify gamma and lambda differently because they're going to be calculated and used in different frequencies. So they still have their separate effects. But then we're also going to combine them with this weighting eligibility trace function, this counter. Right, so this function here is always going to be some number. It could be greater than 1, right? It'll always be greater than 0. Right? But it can be definitely greater than 1. And it could be equal to 0 at the beginning. And that gets multiplied by these other discounting factors we have for the future states as well. And so what we're doing here is we're building a recursive definition where for every state we have an eligibility trace, and if we visited the state right now, we add a 1, right? And we use the previous value of the trace for that state. And if we didn't visit it, we just keep it as is, but we downweight it by gamma and by lambda, right? So it's a future state, so it's get downweighted by gamma, and it's a backup that we're taking using this outcome to kind of weight our updates, so we want to use lambda as well. So why are we doing that? We need one other term that we're going to use in order to get us to our usual value update, right? So we're going to define small delta. That's this versus capital delta is the place we actually get your capital and your lowercase Greek letters. It's going to be just this fundamental kind of calculation of we got a reward right now. We take the difference between two adjacent values from our value function, so what we expected to get in the next step versus and the current step, and discounting that future step by gamma. And essentially, this is the signal that we want to send back over time, right? This is what we learned. We got some reward, and now we want to subtract out the junk value that is about the current state, which was wrong, but keep whatever we else had about future steps t, and discount that by gamma, and this kind of encapsulates the message that we want to send back. If we get to some state st plus 1, some number of steps back, as discounted by lambda, need to hear about this reward, right? That's the whole idea of this n-step approach, but now we're weighting it by lambda, right? And so you can think of essentially gamma and lambda controlling how much this message gets degraded backwards in time as you're learning. So remember before we had our delta V being something that used alpha and R and V, right? And so it was finding a difference between the return over some number of steps, whether it's based on lambda or based on n. And then we're doing this for the same state, obviously. And then subtracting that and weighting it by alpha. Now we're having something where the alpha is still there, but the gamma, the delta, and the epsilon still have these, right? And so epsilon has lambda in there, and delta has gamma in there, and epsilon actually has gamma as well. So all of those forms are now encapsulated into these other things. And really, remember delta, that's why it's named delta, it really is just that difference of the values that we have here, right? So it's just the difference. And then the trace is this function that decays over time with all our temporal weighting parameters rolled into it. And so now our update is just going to be this, these three things all together. And we get the same form that we had before. So if lambda is 0, we essentially get TD 0 because these updates will never be used. They'll always be 1 or 0 or nothing. And if we set lambda to 1, then we'll always be keeping all of them and throwing away nothing, right? And so they won't decay at all except for the gamma. Right, so you still have to decay that future states don't have as much input on the future, on the present updates, but the lambda decay wouldn't be there at all. So you'd keep everything. So if you implement this to do Monte Carlo, it's actually still better than original Monte Carlo because it's still working incrementally, so you don't have to wait till the end until you literally get a reward in order to update it.